So let's continue. Where we are? Okay, we're the diffusion model. So let's do the last computation. So let me just recap like in 30 seconds. So what we have basically is, again, we start from this point of view of that you want sample from an objective P. That in our case will be this P data. And we want to follow the same type of methodology that people have used classically, is that you sample from something that is easy, let's say uniform or Gaussian, and then you transform the data so you can sample from the objective P that you want. Now the issue becomes, what happens if you don't know, you don't have access to the distribution that you want to really sample from? So this is where like a diffusion model comes in. And the idea in this case is a little bit the other side. So we saw Langevin dynamics. What you do, you start with something simple and you evolve until you start from get the P that you want. In diffusion models, it's a little bit the other side. So you inject noise until you basically have something Gaussian, and then what you want to do is go back. So you sample Gaussian and you try to come back. And the idea in this case is that you start from the SDE that you have on top, that this will add you noise under suitable F and Gs. And now it's the point like, how do we come back? The easiest way is to compute what's called the flow, the probability flow, that is the equivalent ODE for this case, in which looks basically that. X dot is equal to sigma dot sigma, and you have the score function. Now, and this is reversible, so you can go back and forth. The problem becomes like we don't know what this log P, nabla log P it is. So one way to go around that is basically go to this formula that basically give you a way to compute this log P by relying on this denoiser. And so after all these acrobatics, what we have basically reduced our problem to, can we find a denoiser that actually can help us? Now, I just want to be sure, this formula looks a little bit like coming from nowhere. So I will try to go through a quick example. Well, it's not going to do that quick, but a relatively short example to show you that this is actually the case. And let me put this, turn this on, so it's easier to read. And this is, well, sorry. And the phenomenon that I'm trying to go here is very similar to the equation that you have now on the screen. So this is your forward SDE. So this is basically what you have there with a few modifications. And then what you want to do is go backwards. And you could see in this case, it's a different realization that has a few more terms. But it's still what you want to compute is the score function. So in both cases, we need to compute this quantity. And how we're going to do it is basically relying on the 2D formula. In this case, we'll just use a simple case, well, a simple example to show you that this formula actually it is indeed true. Okay, so let's do. So, for example, we would try to suppose like normally we'll call like a non-parametric problem. So you have data. In this case, you suppose that you have n points yi. So you have points in some space. In this case, we're not saying. And what you have is the empirical distribution of these points, seen as a direct deltas, and properly weighted. So you will see this also in the computer lab. So let's then compute our marginals. So if you recall how this works, marginals that would define like P of x comma sigma, which is basically the marginal that goes into that log P, is defined as a P data. I mean, it's not defined. It's computed by P data convolved with a Gaussian of, in this case, you have S x0 by basically 0 comma sigma square I. And this is evaluated at x. You can see x here is the one here. Sigma is the sigma squared that goes in there. So everything is well defined. So in this case, this is fairly simple. So just compute the convolution. So you have, what do you have? P data is just this little monster there. So I is equals 1 to n. Sigma, let's do a different integration. Let's do z minus yi. And then you have, this is just a Gaussian. So I don't want to bother with the constant. So just call it c. We can just do it. The notation that we had before, this is going to be x, comma, z, comma, sigma square I. And this is going to evaluate x. Again, the convolution here is done by basically having this x minus z. You can see this is fairly straightforward. So you have a Dirac delta. Every time that z is equals to yi, this is the only thing that survives. So this is nothing more than the 1 divided by n. Sum I is equals to 1 to n of the Gaussians here, x, but center in yi. And that's it. So basically what you're doing is you treat your initial condition as a point, and then you start to add a Gaussian around that point. So again, you have to think of this along the lines of a heat equation. So if you have a heat equation, you have a bunch of Dirac deltas, you evolve, and then basically you have a Gaussian center at each of these points that start to slowly to diffuse. Questions? No? Okay. So we're here. So now we know exactly an analytical formula for px of sigma. So we can just go and compute our score function, right? It's nothing more than just the gradient of log of p sigma. Wait a second. Yep. So just compute this. Just compute this. Wait, what is it? Okay. So just do that, right? I mean, what do you have is like you have lambda x log p x comma sigma. And again, this is nothing more than lambda x p x comma sigma divided by p x comma sigma. Now, you can just go further. You have, this is lambda x of, okay, this is going to be annoying. So let's do 1n sum of these Gaussians n x comma yi comma sigma square divided by the same thing, 1 divided by n sum x yi comma sigma square. Again, just cancel things. Let me put this one a little bit further. And then what we have is just this gradient to compute. So this gradient just go inside the sum. So we have the only thing that we need to do is sum of these guys here. Now, the only thing you need then is to do a gradient of the Gaussian. So, okay, is this clear? Questions? No? Just, okay, gradient of the Gaussian. So let's just do that. So what do you have? X, you have a C that I don't care because it's not going to happen, nothing with that. E to minus 1/2 x minus yi. Divided by sigma square. So you go into this, I mean, you have exactly what you had before. So x, yi, comma, sigma square, multiplied by the gradient of what is in here. So minus 1/2 x minus yi, and I'm missing the squares everywhere, sigma square. And this is like that. This you know how to do. So normal x comma yi sigma square, and this is nothing more than 1 divided by sigma square, x minus y, 2 comes out, then you have the minus here, so we have yi minus x. Just put this inside here, and what you have is nothing more than let's see, sum of n x comma yi sigma square. So this one goes in here. You have another term that is outside the sum. So x, and well, you have 1 sigma square over all of this, and then you have finally sum of these Gaussians, x comma yi comma sigma square. And I think this is correct. Just to be sure. I mean, you can tell me if there's a mistake. Again, what you can do is simplify this a little bit further. You eliminate this, and what you have at the end, let's put it here, is basically this guy in this point here. So you have sum of all these Gaussians, x, yi, sigma square, yi, divided by sum xi, yi, sigma square, minus x and everything divided by sigma square. Okay, clear? Just computation. I mean, if you're in the French system, you most likely went through this a lot of times. So, okay, so we have that part. So now we, this is what we want to get. Now let's try to compute our denoiser now. So this is for the log, the square function. Now let's do the denoiser. So denoiser. So again, this is basically d x, sigma, and then you want to have x naught, that is your original image. And how you want to do this is by solving the following loss function. So you have, let's call it curly L, d, sigma, and this is going to be the following. So the expectation that y follows the p data. I mean, you want to be able to basically denoise your data. Expectation of the noise following a normal distribution 0, sigma square. When you want to introduce noise, that is dependent on sigma. And then you will do, as you expect, d y plus n, sigma minus y squared, right? So I give you y, I will add noise, and then you have to give me back the y that I gave you beforehand. Now, let's do a few reparameterizations. So what is the reparameterization that I would like to use? You have y plus n. N follows a sigma square. So what I want to do is basically change this a little bit. So what you will have, let me put it here, the expectation. So y follows p data. In this case, you will have the expectation, or let's change x. X in this case will follow a normal, but centered in y, and sigma square. And then the loss is going to be slightly different. So dx, sigma minus y squared. It's clear. Is this fine so far? Okay. So now it's start to get a little. Okay, let's see what else we need here. Okay, so basically we can do the computation for this guy. So this is going to be well, the interval. So y p data going to be integral of this thing x, sigma minus y, and this you will add the PDF in here. So you have x, y, sigma square dy. Okay. Now, last thing is what is this guy looking like? So this guy p data is nothing more than all our Dirac deltas. So you can add just this one in this case. So what you have is basically 1 over n sum of what? Of Dirac delta. Let's see. This is going to be y is equals to yi, or y minus iy. Is I is equals 1 to n. Integral, and then you have x, sigma minus y, Messier squares everywhere, normal x, y, sigma square dy. Wait. And then, sorry. This is not dy, this is dx. Sorry about that. And this is, we have a dx here. I mean, integral as well. So now, Fubini, quick. So you want to do, this is dx dy. You want to do dx dy dx. And what happens is basically this guy gets into the here and here. And what you will have at the end of the day is basically 1 over n integral, let's call it in x, of dx comma sigma minus yi square normal x comma yi comma sigma square dx. Okay. Now you want to minimize this guy. So I mean, the advantage here is that now we have something and have a sum that have a sum here. I is equals to 1 to n, 1 divided by n. Now, what do you want to do now is minimize this loss, right? Now, there's a different ways to do it, but the main point is that if you see here, everything, well, if you just fix, everything depends with respect to x. So we can say basically all of this is going to be a loss that depends dx comma sigma. So we fix sigma, and then if we minimize everything that is inside, we minimize our our loss that is up there. So you can basically just go and minimize this guy. But if you see this d, just a number, right? So you recall how the function is defined. Fine is like you give a number x, you give a sigma, you just have a number out that depends on those. So we can just minimize this fix x, fix y, and just minimize for every x, and, x, x, and sigma, just minimize what is the minimal d that will make this function very small. So you could do exactly that. So what you're going to do is you want to minimize, you want to compute d of x comma sigma is going to be, by definition, the argmin of this new function, dx comma sigma, in this argmin in d, right? So the good thing in that is it looks very nice, very convex, so you can just go ahead and just do it. So let's do that quickly. So in this case, we will assume that you have the, this is definitely convex in D. This is your weight, but these are positive, so everything is going to be convex. So you can just go for the first order optimality conditions, and that should be enough. Well, is that clear? Yes. Okay. This is convex, positive, just every combination of positive convection of positive combination of convex functions convex. So just should be fine. Okay. So let's exactly do that. So let's nabla with respect to d of this curly d dx comma sigma. Now we just have to compute integrals, right? So what do we have? We have this is. Can you pull this a little bit? No. So okay, this is nothing more that well, you have the sum, you have d. So sum of I is equals 1 to n of n this x comma yi comma sigma square. This doesn't depend on d, so it doesn't matter. And then you have nabla with respect to d of this d minus yi, and then that's it, right? Square. Now, let's see. Okay, let's. We have space here. Okay, questions. Is this? This is just computations left and right. So then you can do as usual. You do so sum x equals n to n and x yi sigma square. You have one there, and doesn't matter, and this is nothing more than do d minus yi. Right? Simple. Now, what else do you have? So what is the condition that this has to satisfy? This has to be equal to 0. So equal to 0. And now you can think what we can do. Take d, move it outside, take that one, move it to the right. So what you will find is basically you have is d multiplied by some one y is equals 1 to n of n x comma yi sigma square is equals to, you move the one to the right, so you have sum I is equals 1 to n of the same thing, so yi comma sigma square yi, and then this is positive, non-zero, hopefully. D is equals to sum of x comma yi comma sigma square yi divided by sum of x comma yi comma sigma square. Okay, now this, as you can see, depends on x and sigma, and this is fixed for every x and sigma, so you can basically just say this is the denoiser x comma sigma. So what is this telling you? I mean, this is, even though the data distribution is very simple, this is basically telling you what is the denoiser is going to do. The denoiser is going to try to basically compute the denoised version by a convex combination of your data. So all of this is going to live in the convex code of your data that is basically weighted by the distance of x to the point that you already know. Okay, so and there we are finished. Why? Because as you can see, hopefully, is that where it is. So here we have our log. Recall this is our score function. So log p of x comma sigma is equals to this. And to this formula tells us that this is going to be the denoiser minus x divided by sigma square. And now what is this? This is exactly our denoiser. Right? So now, I mean, this is a very simple computation, but it shows you that using the 2D formula there, actually it's not completely crazy. And it turns out that you don't have to do anything crazy to train this network. The only thing that you need to do is to minimize this function, which is much, much simpler on trying to do all the other acrobatics that you need to do with like evidence lower bound functions or a score-based modeling. The only thing that you need to do now here, like compute your denoiser using this, then compute your log like your score function by using 2D formula, and then you're done. Now you can have a diffusion model in a few. Well, it's not that simple, but in a few steps. Okay, questions? No, it is clear. No, yes.
Only a curiosity, can we consider other data distributions except the Dirac delta?
No, of course. I mean, you can do everything that you want. The advantage of this is like everything is analytical. So I can show you with an example that this formula actually holds.
Okay, what are other examples of data distributions?
So in theory, you could do whatever you want. However, when you do sampling from from really data of images, you do have just direct deltas. The difference here is you see that your denoiser is basically a kernel function, because you have to carry out all the data that you have. And this, for I don't know, just think about like ChatGPT. This is going to be trillions of tokens. So you want to basically compress this with a neural network. Is that clear? Or?
Okay, thank you. Yes.
Questions? Now waiting that the enjoying that the microphone is running. No? Okay. No. So what else? So I just wanted to tell you that, I mean, in this case, basically we are going to the second version. So we want to train the denoiser to run our diffusion model and then leverage this formula. You could do try to learn the score function directly. It is normally more involved, and it's a little bit harder to do in general. You can do just go try to get the noise from the sample. But I will try to convince you that the easiest way to do this is just compute the denoiser by using the formulation up there. So I don't want to go in more details because if I go in more details, it's going to be even more complicated. But I hope that at least I gave you kind of the main idea, is that you compute this score function using the denoiser, and then you will do you can run the ODE backwards. Or you can also run the SDE backwards, as people like Son and company do. So basically, now that you have that thing there, you have the score function through this formula, you can run this SDE backwards. In general, quality of samples is better with SDE than ODE, but in general, I mean, now it's up to you for the application, which one you prefer. Okay. So now let's go to an application of this. So the application that we're looking for is something that calls like a climate downscaling. So what is the main idea of climate downscaling? This comes from the fact that to really get the climate that is going to happen like in 50 years, you need to leverage simulations. So people have like these gigantic models that they have to run for many, like 100 years. So it means that the computational burden is so high that you cannot run a high resolution. So you run something very coarse with a very large time step. It's going to generate something with their own biases that is going to give you hopefully some ideas of what's going to happen in 50 years on the different carbonization schemes. But the point is that they have a bias because they're so coarse that they have biases because they cannot capture the small scale dynamics. And the second thing is that the output is useful, but it's not that useful in the sense that there's so many things that are very local. For example, if you think about like wildfires or flood, or those are very local with respect to like a small geographically localized event. So for example, this is CIMP data. So you could see like basically Marseille is just like, I guess like all the Côte d'Azur is just basically 1 pixel around there. But this is it's not very good. So you want to be able to get like a more resolution. And the question is, becomes like, how we can get more resolution? We have to run this very, very expensive model that is almost impossible to run a high resolution. So is there a way to take a snapshot that is coarse and add basically features, geographic features to it? The answer is yes. And this is basically what is called climate downscaling. So you can think that this is basically a super resolution problem. So I give you something that is coarse. Can I generate something that has a high resolution? And there's so many methods in the CS community that they do exactly this. So you have this cheetah here. I don't recall exactly what these images are for. So I think the first one is the original. No, the middle is the original. And the different ways of basically getting like more resolution. But the point of this is that in our case, you have a bias. So if you kind of don't understand what super resolution does, super resolution can be thought as a frequency extrapolation. So for example, you have your samples here that is low resolution, and what you want to do is basically guess what are the higher frequency components of it. So that's why when you got the cheetah, you go basically something that is very blurry to something that it has more features, like more crisp figures, features, because you can basically try to guess what the extrapolation, the high frequency content of the image it is. But for that, you have to assume that basically your cheetah is on your training set, or is somehow in the distribution. What happens if you give like the image of a pig or a boar? It doesn't know how to do that because it doesn't have the correct bias already. So this is exactly what happens. So your climate simulation will have a different bias or something that you have to expect. So in this case, this problem is not just super resolution problem or upsampling, it's also biased. So you have to do 2 steps. You have to take your board, for example, make it look like a cheetah, and then upsample the cheetah. I mean, it's not that, but it's kind of similar. The issue in this case is that you don't have paired data. So in this case, normally people will train this by I give you a cheetah that is high resolution, I give you like a blurry cheetah, and then I ask you the network to come up with the good one. In this case, you don't have, because you don't have data of high resolution climate in 50 years. So you somehow have to basically move it to something that looks better today and try to leverage something that is a high resolution data that you have right now. Climate is too hard, so let's have something simpler. And in this case, what we'll do is like just fluid simulations. So there's a fairly good and fairly well-known benchmark that's called the Colcomore flow in 2D. And what we'll have is basically a low resolution, so this curly Y there, and then you have a high resolution X. So X is going to be trajectories computed with a spectral method, high resolution, everything that you want. Y, you can think about like something finite volumes, very dispersive, very bad, things that you learn in first year of university that you know they're pretty bad, but still you will do it. And the point is like, then how we move from Y to something like move like X, something low resolution, low fidelity, to something high resolution, high fidelity. So what we reckon here is like in the underlying point of our work is basically, at the end of the day, they're trying to simulate the same thing. It's a fluid simulation, so then the line physics it should be the same. The difference is that the numerics produce the bias. So you should have a way to go from the numerics, the good numerics, to the physical problem, from the bad numerics to the physical problem, so there's a map that basically connects those two things. It's unknown, but you think there is a map. So, and then we call this map C. So C is basically takes you an X, and you can connect it with something that is a low resolution. The problem with this map C is unknown. And the second one is how you really formulate this problem in a way that you can leverage sampling. So as you can see, Y has a very low resolution. So it may have that there's many X that have actually, after you apply C, you can have the same low resolution. So basically, there are many possible configurations that if you take the average, you're going to give you the same average. For example, our best example is in San Francisco. So in the Bay Area, you have a pretty different temperatures in San Francisco compared to the South Bay or Berkeley. And it happens that if the full Bay Area, the temperature is higher, it means that the San Francisco itself, the temperature normally is lower. So there's many configurations in which you have the same mean temperature. So that's why you want to do this procedure probabilistic. So what I mean here, instead of trying to just have one image, you will try to sample following this probability. So this is basically where the probability of X's, imagine like temperatures in San Francisco, such that the mean is equals to something that we see in I don't know, 80 years with our model. So there's two problems here. One is you have to compute P. Second, C is unknown. But even if C is unknown, you can do a few things about that. So the first thing is like you can introduce a factorization. So C is going to be a transformation T inverse that we will do in a moment, composed with C prime, that you can have something very simple. You can have like an average operator, or you can have like something like mean operator, something like that. And then you do a factorization. So basically, you can go from here to here using C. You can go back probabilistically using this sampling from Px given Cx equals Y. Or basically, you can go do a detour. So you can go from this Y, go to this Y prime, that is basically low resolution but high fidelity. And then from this Y, you can go easily to X. Now, I mean, this map is C, you have no idea what it is. So you can at least add the minimal things that it has to satisfy. And in this case, what we want to satisfy is that the push forward of this transformation basically preserves statistical information. So basically, if you have a distribution in U, and you push forward through, in X, and you do a push forward through this map, you basically have to get the correct probability of distribution in Y. So this is, we think, is the minimum you can ask. When you transform these things, just.
What is Y prime again?
Okay, so Y prime is basically you take all the Y and you apply this map T inverse. So this can be done, these are the two resolutions. So y prime has the same resolution, but have different biases. So what you do is basically debias first, and then you apply the upsampling operator. So let me see if I have a new one here. I mean, you already see this one. So basically what y does, this is basically y, this is y prime, and then you complete with the other one. So basically what you do is you debias first, you move all the information to the correct space, and then you add, you complete. Okay, questions? Yes, no? 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 Okay, let's continue. So there's two steps. One, you need to sample from your distribution, and the second one is you do debias. So the sampling, I guess you know exactly, you've already seen this picture before. You want to use a diffusion model, and the idea of this is why. So the main reason is why is the qualities are normally very high. The samples are high quality. You see the panda and the corgi before, and the good thing is like you have a high coverage of the distribution. So you can claim that a regional, like in a region, for example, like Marseille, climate in 50 years is going to be fairly similar, but different distribution. So you have much more cold, like hotter days or colder days, but it will look roughly the same. It's just the distribution is going to be different. So you want to be able basically to capture this extreme event, or like extreme distribution, and then push the distribution the 50 years toward those values. And then it's basically we can do on-demand sampling, as you've already seen. Now, what is the issue then? There's not issue, but the main problem is that you want to do, you don't want to do just P. What you want to do is P of X given some like a C prime X of Y. So you need to add an extra step. You have to be a conditional probability. So P of X is simple, as you can see. You just have to compute this, well, simple, like a log P, and then you run your model. But if you want to also add this constraint, there's start to get a little bit tricky. Why? You can either do this by what's called a priori. So basically, you inject on your denoiser the fact that you have a Y, for example. Or what we try to do right now is what we call a posteriori or inference time conditioning. So basically, you train this log P as you stand there, and then you're going to do is going to make a modification afterwards. So the easiest way to consider this modification is to go back a little bit to what is this log P means. So you recall when you have the John-Givan dynamics, this log P was basically giving you moving you to the regions of high probability. Recall, if you recall quickly, basically, you have it there, right? X dot for the sigma. This is basically is going to move this X dot into the regions where this log probability is higher. So you could do is basically modify. I'm going to modify this to actually go into this particular that hyperplane. So you just train where you have. You do a small modification. Normally, people will call steering, and you can push your problem into that direction. And people have done this in scientific computer, in CS. So typically, you have in painting. So you have a corgi. No, not corgi. This is oh god. This is Lassie. No, what is the name of this breed? A border collie. So you have border collie. You remove the middle, and then you try to basically get in the middle, reconstruct what is inside. So this is very bad. But if you do it properly, you can do, for example, super resolution. You have 32 by 32. Then you say, well, every 2 pixels of this image are going to be the same as this image. And then I will let the network fill the extra pixels. And the same here, right? You say every 4 pixels of this image, it will be 1 pixel of this image. So basically, you have a mask. And this actually works fairly well. So this is going to use. And And the second issue is the bias. So you have two things that have different distributions. So this again goes very similar to what we discussed was discussed yesterday. What happens if you have two distributions? So you train, for example, with everything that is a dusk. And then I telling you that, well, you have to do upsampling with something that is in a dawn. So if you try to just do it one shot, you will complete garbage because you're completely out of your distribution. But what happens is you can basically move a little bit the dawn to dusk and then do the upsampling there. So this is basically out of distribution. And the idea of this is basically using optimal transport. So again, you have something that follows this distribution that you don't want. You want to modify it, and then you want to do upsampling. If you try to do upsampling, basically fill the extra Fourier coefficients here, is going to be a disaster. So this is basically something that happens in this case. So it's going to be completely unrealistic. So what is the point here? I mean, the easiest way is just to do optimal transport. So this T, we haven't talked about this T. This is the biasing term. And what you could do is just compute this minimization problem. Olga talked about this a little bit, so I won't go to the details. And you can compute this T that satisfies this minimization. And more importantly, you can force it to satisfy this T, the push forward of uy is equal to the push forward of C prime over mu x. So in this case, you maintain the statistical information. And if you go through that, then basically you have these two steps. So you go from this y to the UD bias to y prime using the optimal transport, and then you go the other way around. Wait, did I have? Okay, sorry, I didn't show it. So this is kind of the point. If you have this cumulonimbus in a dawn, and you want to move it to y, so you can use optimal transport to make it look that the picture was taken at dusk. And now you are in the correct distribution, and now you can upsample. Is that clear? So basically, you're trying to manipulate your data in such a way that your algorithm has is in distribution, so it has a much better time trying to do upsampling. And then you can do that. And then you have two steps. First, you debias. And then when you have your debias, you can just use your probabilistic model to compute samples that look realistic and satisfy the correct statistical conditions. Statistical properties. So I think that's the next example. So let's do the same thing. So you have
Can I ask you a question?
just
Again, your C prime, how do you construct that, please? I'm sorry, I keep on
oh, C prime. Okay. So to the people at home, the question is, how do you build this C prime? So this C prime is, you can take it as whatever you want. So this is basically preservation difficulty. So you can choose a very complicated C prime. It has to be linear for reasons that it's much easier to do conditional sampling if the C prime is linear. But then it's basically, you can have something that is more aligned to the modeling, and you shift more, less burden to compute T, or you can have something that is very simple, like like a decimation mask, for example. But that,
it's not learned. Is it learned?
No. C prime here is a modeling choice. So you can either choose like to do an average, local average. So imagine like, I don't know, you take the temperature of all Marseille, or you take the temperature like a one particular point. And that is really modeling based. Some people like one way or have different ways to do filtering, depending on the location of the Earth and so on. Did I answer your question? Okay. Questions?
Other questions before you proceed?
No? Okay. So again, two different examples. Okay, this is wrong. This is KDV. It's not called Gomorrah flow. I just realized that. So there's, sorry, no, sorry. It's okay. It's correct. No, it's not. The figure is KDV. It's not Kuromoto-Sivashinsky. I'm sorry about that. I just realized that. So Kuromoto-Sivashinsky is a very chaotic system. This looks bad, but it's not chaotic per se. And then the other one is a 2D Kolmogorov flow. So this is basically looks a little bit like this. So you see, it's fairly has like all this wiggle and so on. So what we will do is we'll run these two models a very low resolution. So you can see here the input is 8x or 16. Well, I mean, it's an eighth. So basically, one every 8 pixels, one every 1/16 pixel. We're going to run this using finite volume, first order, like very, very bad, the same thing that you learn in conservation laws. And your reference is going to be a high resolution spectral method. So this one is going to be way more expensive than something at the left. And I'm going to take these inputs and we're going to try to do upscaling. So our method is here in red. So you have a few different things that you could do. So you can try to correct B. This is a still low resolution. You can have cycle GANs. You have different interpolations, like a tricubic interpolation, and use like a vision transformer, and so on. And in general, we get the best resolution in this case. It's the most realistic. Okay, these two are the same, or look very similar, because this 16x is basically the one from X that is downsampled by a factor 2. So this is basically, again, it's an 8 and 16x super upsampling. And you can see that we cannot preserve the main features of the flow, right? I mean, you have this very, very big, like kind of like flows here that kind of correspond to features. At this point, they're placed in general in the correct directions. And then you can do Denoiser spectra. So this is kind of the vanilla version to be sure that at least things look alike. And you could see that you have the true, that this is how the energy decays as you, for the different for modes. And if you don't do anything, you have this red that is, sorry. Yes. And if you don't do any, what's called, you don't do any biases, you have this green one that is pretty bad. And basically, if you add this debiasing plus the super sampling, the upsampling, you are right next to the correct energy spectra. So basically, you have the correct features. You have the correct, statistically correct, I mean, yeah, statistically correct features. Now, you can do exactly the same with other methods. So this is the log energy. So basically, the closest to zero, the best. And you could see, I mean, we could try a few different things, cycle GANs, different tricubic, vision transformer. I mean, we threw everything that we think that it could be useful in this case. And we're much better. And particularly when you have a more aggressive upsampling. So left is 8, and right is 16x. 8 cycle GAN is fairly competitive. It still is not as good in high frequency, but for 16x, it completely goes crazy. So having these two steps actually helps a lot to get something that has the correct statistical information. These are other very similar, or very typical measures of distributions. So you have basically how well the constraint works. You can see our results are in red, score very well. How much sample variability do you have? You still have a pretty good amount of variability. So what I mean with variability is, for example, for the same constraint, how many different samples you can generate. So imagine, like, for the same temperature of all France, how many regional differences you can actually you can generate. And then you have like mean energy, log energy, weighted, unweighted, different ways to measure it, and the typical like KDE, KLD. So this is another way of measuring difference between distributions using the kernel density estimation and the KL divergence. I mean, Motorline, we're the best here. I mean, otherwise I wouldn't be showing you this, right? And you can do a few other things. You can really go crazy and go really like coarse. So this is like 4x4, and still you can generate something that actually looks as it should look. And then you have the, I mean, okay, this is different realizations. So B to G, so you have the same constraint, and you sample, you different samples. And the point here is that you are exactly correct on the point that you say that you want to be what you want, and the rest you just let the imagination of the future model to run through. So in this case, this gives you a lot of variability. So it leaves you the possibility to really explore things that you haven't seen before. And of course, as you go up and you add more constraint, things become, I mean, less variable and more, they look more they should look like. And okay, this is almost the end. Well, not too bad. So, but we want really climate applications. So this is what's called like the, I mean, I don't remember community X something model, a sphere model. I don't remember what the S stands for, but this is a typical model that people use for try to see climate in I don't know. This is, I don't even remember. This is under one of the CMIP carbonization protocols, so I don't remember. But anyway, this is supposed to be a snapshot of the 2-meter temperature of the Earth in 50 years, or no, in 250, so 27 years. But the product you don't see much, right? I mean, okay, you can see the contents a little bit, but the other thing is like it was very weird because this is centered in the Pacific. Anyway, so for example, you cannot see much of the East Coast. You can, I mean, South America. You can see maybe Argentina. You have Brazil is not really there. Australia is going to be hot, maybe, but you cannot see that much. But using this technique, I mean, this is work in progress. It's not still great. You can just have all these extra details added to the image. Okay, I mean, you cannot see that much actually. Well, anyway, it's supposed to be much better. So you have like, I mean here you see the Red Sea. You see a little bit the Italy is there. You can see the Great Lakes there if you really squint. Anyway, I mean, this is 5 times resolution, and I'll give you much more details. It's much crisper. Anyway, this doesn't look very good. Okay, I have to change the palette next time. But this seems to work so far. It's still work in progress. We can do much better. Oh yeah. Okay, that's good. And so this is the conclusion. So this part is basically high fidelity samples that you can correct with bias. So use 2 main techniques. One is diffusion models to basically generate the samples, and optimal transport to debias these things. And I would claim that those are the techniques to be used in this case. And the main idea is like, I mean, that you can basically just train one diffusion model, and then you can add this extra conditioning on inference time, which is something that you will normally would like to do. And after that, questions. Thank you very much. And I think, yep, questions there.
Just a quick question. First of all, very impressive results. But for the Kolmogorov flow, how many samples did you use for your training?
Around 2,000, I think.
So these are at different times or at the same time snapshot?
So we just took like a bunch of like different snapshots, and then
2,000 was enough for the diffusion model?
2,000 was enough for the diffusion model to have correct like thing. Although you have to be a little bit, you have to take the samples far away from each other. So basically, you take a snapshot, you wait until basically it's not correlated anymore, and you take a sample. But again, the Kolmogorov is a little bit of a kind of cheating questions, because you do have like a low dimension manifold on an attractor. So you are able to basically, with 2,000 samples, you can sample fairly well. Thank you.
Thank you very much for the talk. Actually, I have 2 questions. The first one is, are you training 2 steps, like one for the bias correction and one for the upsampling, or is it everything done in one step?
Okay, so that's a very good question. So the idea in this case is that what you want to do this inference time conditioning. So what I mean with this is that you train PX, just that, once, and you just fit it. I mean, you just fix it. And then when you do conditioning, the sampling, you have to modify this core function, basically what you have there. But that you don't need to train. You just basically add an extra term that can be done offline. Then for this guy, you have to solve this problem. But this is a different problem. It's not related. So the only thing that you need to do is basically to compute this t. So in this case, you could do everything together, but in general, you want to do it in 2 steps. Why? Because you may want to change this c prime. Is that clear? Or?
Okay, so it means that you have like supervised labels of y and y primes?
No, because this is you have samples, but you don't have one-to-one correspondence. So that's why you have to solve. You have to do it in a basically distribution type of approximation. So you know you have samples. You want to see what is the transformation that takes me from this distribution, right, this set to this set, and preserve the statistical information. And the one that ensures you that is the optimal the transfer map. But you don't have one-to-one correspondence.
Okay, thank you. And my second question, what about climate downscaling?
Mm-hmm.
Excepting from like recovering boundaries, do you have any way to know if it makes a physical sense, the extra resolution you are adding? Because we can see that it's more resolved, like we can see the boundaries between land and sea, as you mentioned, but the pixel you are adding, for example, on the land very close to the sea, can you evaluate if it makes more sense or if you are just adding resolution that maybe doesn't have a physical meaning?
No, yes, you can, and that is basically because normally that correlates with topography. So normally when you have a sea and you have mountains, you have a different variability. So you can check like geographically where the variability is the highest. And you can do like a topography based like minimum discrepancy. And you can check that it's actually, physically it's a little bit, the words a little bit, physically we don't know, but statistically we can say that actually makes sense. And also you can say physically that you have an interface in which causes the change in temperature.
Okay, thank you.
Did I answer your question? Okay.
I have a question more about like the diffusion we use as to like do this sampling.
Mm-hmm.
Would it be worth it to try like a second order diffusion like underdamped, especially for, like, from a discretization perspective, since we can have like second order integrators relatively easily? Does it make a difference or?
Yes, you can do different things for the diffusion model. So underdamp, people have done it. The issue with underdamp is it becomes much more expensive because in general you have to do an exponential integrator or something high order. And then you have to think about is these choices of sigmas that I put there, I didn't really tell you what they were, but it turns that sometimes when you're really close to the end or closer to zero, they're pretty large. So you have to do adaptive schemes to actually integrate them properly. So the question is like, yes, you could use those things, or you could have a very good integrator between 0 and 1 with the correct, basically, when you get close to 0, you have more point in a certain way.
Because you're not explicitly integrating from 0 to 1, you're like just using Euler-Maruyama?
That's an integrator as well, right?
What?
It integrates too. You integrate, well, it depends how you define the integral, but yeah, you can do Euler-Maruyama. The issue is that still you need to have different discretizations in time.
Because my question is like, are you solving it? You solve it ST explicitly and you just use the explicit solution, or?
No.
Use a numerical integration.
Well, just think about you integrate using Euler-Maruyama, but the point is like the time step. Yeah. It depends on t. Okay. So as you go closer to 0, normally you have these guys here. The sigma becomes smaller, so you basically your problem becomes stiffer in some sense. So you have to be careful about that. And then I don't use this. I use something much more complicated. Yeah.
Thank you.
Thank you very much. Super interesting to see advancements in climate downscaling from math perspective. My question is similar to Fanny's one. When you debias climate simulation data from the community or system model, for example, how do you validate this? Because even the climate models, we know that they have biases, and there's a lot of discussion going on. You said you validate it against maybe statistical data, but the statistics change, right? Like that's the point in climate. Okay, so fair enough. So there's two ways to thinking about this. So I agree. If you have global something that I showed you in the picture afterwards, it's very hard to claim that this is correct in the sense because in general you don't have enough variability global. So for example, you can have parts in like Australia is very warm, and India has a monsoon or things like that you haven't seen before. So that is much harder. But if you go like a regional downscaling,
you have much more variability local. And then in that case, you can do you can assume that basically it's going to, I was saying before, it's going to look similar, but you have different statistics. So that's basically what we'll try to match. And what you can match is basically you have different different CIMP models that you can basically play with. So again, it's not a pure, it's not a, let's say, it's not a mathematically correct way of measuring, but it's statistically what I had the impression, at least, or you can correct me if I'm wrong, that geoscientists tend to just go for the statistical, and I don't know, and then they do then. I mean, this is just 2 meter temperature, but you can have more than one. You can do like humidity, or you can do like geopotential, and those ones they do have a much stringent correlation. Did I answer your question?
Any other question?
Thank you for today's lecture, very interesting. And my question is about the first part, when you considered a neural ODE to train the parameters for the neural network that returns your solution. How do you choose the network gamma B? Do you have what kind of architectures have you tried? So
gamma or lambda?
No, not the encoder. The network that trains the parameter
gamma
beta.
You mean the dynamics?
The dynamics for the dynamics of the parameters.
Okay, yes. So I mean that's a trade-off between you have to balance the expressivity, and you have to balance the number of parameters. So you could do just an MLP. It does work, but you will use a few hundred parameters, no, a few million parameters. If you do like a UNet that normally has like more structure, you can go to like 500,000 or something like that, or you can go even lower. So this is, I mean, my answer is you have to try different things. You can go just for MLP, it's going to work, but it's going to be much harder to make it convert to something that you like. I don't know, did I answer your question?
Yeah, sure, thank you.
There is no more questions, so we can...
So actually like a question about the climate downscaling. So I mean, what I've seen people doing so far is all this quantile mapping. That actually quantile mapping is a kind of a one-dimensional optimal transport. But you preserve the statistics for only one point, but you don't have any correlations between neighboring points geometrically. So what I have here is basically add also the geometrical spread between points, not only point-wise, but basically a full statistical correction. So you do quantile mapping, you only basically correct point by point. And that's when. So we compare with quantile mapping, and we're way, way, way better. Yeah, well,
So with this, we can end again.
thank you.